Well, first of all, I was saying thank you again to the organizing committee and Vasilis for the invitation to come here today to talk to you. I'm very much honored to have this first talk, this first plenary dedicated to the memory of Ioannis Seidiadakis. I didn't have the pleasure to meet Ioannis myself, but I understand that he has been a very important person in the history of astronomy, and in particular radio astronomy in Greece. And my talk is actually going to be devoted to this specific of high resolution radio astronomy. And that is BLVI. BLVI, like very long baseline interferometry, that is the main work at the Institute JIVE, where I am working now. So this is I will try to go a bit faster than I thought because of time, but this is the contents of that I expect to do today. A very short basic introduction to radio astronomy for those of you who are experts in other fields of astronomy, and very specifically an introduction to BLVI, and then some scientific results in many areas. Sometimes we want to call this in the context of what is it that BLVI can do for your research. And I mean this because BLVI has impact in very different areas of astronomy, and often this is a complementary view to the physical problems that we are being studied with other techniques. And just to end, a bit of the future of BLVI, and in particular, what could be the possibilities to develop BLVI in Greece. So for radio astronomy, of course, is a view of the universe on the radio waves that we receive from cosmic objects. There are several ways by which this electromagnetic radiation, the radio radiation, comes to us. One basic reason is because objects in the universe have a temperature. Therefore, if we would study these objects like black bodies, we would see that the spectrum of the black bodies has features depending on the temperature of the object, and the coldest the object is, the more to the low frequencies the peak of the emission becomes. So we can see here, this is in hertz. This would be then 1 gigahertz is 10 to the 9. This would be radio waves in this area, and we see here that the coldest objects in the universe have the peak of their emission at radio frequencies. Now, then if it were for thermal radiation, we would be studying with radio astronomy these cold objects. And one other thing is that, as you see here, the intensity of this radiation also is very low. We used to measure radio astronomy radiation in Janskis. And Jansky, as you see there, is 10 to the minus 26 watts per square meter. And that 10 to the minus 26 is such a small number that it is said that all the energy received since the time radio astronomy started at the beginning of the 20th century, all the energy received by radio telescopes is less than what you need to pass one page in a book. So it is really very weak emission, and that also poses some conditions to the technical and the protection zones for radio astronomy to be observed. So that would be one of the reasons for observing with radio astronomy, the thermal. The other one that is very important and very significant for high resolution studies is other non-thermal emissions, in particular synchrotron emission that happens when electrons move in a magnetic field. And by this, they emit, by the movement in this magnetic field, they emit photons, and these photons come to us and we see them as radio waves. the synchrotron emission, it is received at every frequency. So it is, in a sense, a continuum emission, but it is not of thermal origin. It's actually, as we say, of non-thermal process. This would be like some of the cases of continuum emission. Then we would go, of course, to the line emissions, spectral line emissions, which are also very important in radio astronomy. The most, let's say, popular would be the emission of neutral hydrogen. And this is because hydrogen is the most abundant element in the universe. Therefore, even if the emission is not very intense, because there is so much hydrogen, we see it everywhere. And it is due to the change in spin of the atom of hydrogen. When the spin of the electron flips, it emits or absorbs a photon at the frequency of 1.4 gigahertz, which is corresponding to a wavelength of 21 centimeter. Now, when you observe the universe at this wavelength of 21 centimeter, you can see a completely different view of the cosmic objects. In this particular example, you can see a galaxy in optical in the left, and you see the very same galaxy when you observe it in hydrogen gas in this frequency of 21 centimeter. And of course, well, what you see is much more information and very complementary to what you were observing in optical. Therefore, the combination of this optical and radio in this particular object, the combination of these studies is extremely important. So hydrogen is one. Well, this is another of these examples of how you can complement the optical emission in the left of this of this galaxy, which is M87, and you will see how the big, huge structure of M87 starts at the very center of a black hole, that we will see later, and this jet that is emitted can be seen both in optical and in radio, and as we say, we can complement the two images. Now, this was for hydrogen. As I said, there are many other, more than 200 molecular species that have been found in the cosmos. And from many of them, we can observe their radio spectrum. This is, in particular, this is one of my favorite, which I have been working for some time, which is the molecule of silicon monoxide, SiO. SiO has its spectrum, its energy level, and it has a specific process happening that is called the Maser process, microwave amplification by stimulated emission of radiation. So due to fortunate pumping of some levels of energy in this molecule and the accumulation in a higher energy state, stimulated decay of all these energies, all these molecules at the same time, produce a very intense emission, that is the maser. Now, we can observe these masers with very high resolution, and we can get objects, maps of the objects, like in these late type stars, in which if you notice the scale in which this map is happening, which is milliarc seconds, we are actually seeing the inner regions of the outer envelope of the star, which is possibly the only technique in the world that exists that can provide this kind of resolution and detail in these objects. So we will be talking about this in a few minutes, but in order to put this in context, I'd also like to talk about a bit about the technique. And the technique is how we observe in radio astronomy. Now, I will focus on the particular case of radio antennas of the shape, parabolic antennas, which are very good for this range of gigahertz observations. Of course, if you go to much lower frequencies, megahertz, you can use also dipoles antennas or others. But I will look into this, which is quite relevant to the examples that we will show later. Now, if you have an antenna like this, the instrument is sensitive to the radiation that comes from the sky in the direction that it is pointed to in the axis of this paraboloid, and only in that direction. which means that this, the difference with other techniques like optical astronomy is that you have one single point in the sky in which you are sensitive to and you can grab information from. Now, the size of that point, which you could call the angular resolution, which is this beam, the width of this beam, this is determined by the size of the antenna, the D, the diameter of the antenna, and the wavelength of the radiation. So if you go to bigger dishes, you get higher resolution. If you go to shorter wavelengths, to higher frequencies, you also get bigger resolution. So if you want to get very good details in the sky, that is the way you have to go. Go to higher frequencies, which not always is possible because it depends, of course, of your source of information. If it's a spectral line, you cannot negotiate with the molecule, but then you have to get to bigger antennas. Now, if you have extended structure in your object, you have to point one by one to the different areas, and that is time consuming. So there are, let's say, advantages and disadvantages of having this kind of approach. Now, the alternative to that is interferometry. If you want to get much more information and much more detail on your spectra of your cosmic object, you can change the concept of a beam of one antenna in which the size of the antenna determines the resolution, and you can get an interferometer like you can see here, with antennas are distributed, a number of them. In this specific example, you have 2 antennas. A number of them are distributed around the Earth, and then the distance between the telescopes is what determines the resolution. So you change from this single antenna power pattern to this other called interferometer pattern, which, as you can see, the size of the area in the sky in which you are sensitive to becomes much smaller, and the fact that you change from this size of antennas of, say, meters, 100 meters, to distances between antennas of thousands of kilometers means that this resolution is completely boosted. Now, the problem, if we would say, that by using this BLVI technique, this interferometer technique, is that you are synthesizing a worldwide telescope, but most of it is empty. Most of it does not have, let's say, panels in which you are receiving radiation. And you can solve that by having many more antennas covering the Earth and allowing the rotation of the Earth to create these tracks that we could call the sampling of the UV plane. This is the equivalent of the synthesized radio telescope that is being filled up as you add more antennas, and you also allow the Earth rotation to fill the plane. Now, each one of these points in the UV plane corresponds to one pair of antennas looking at the source at one specific moment. Okay. Now, if you see all these tracks, means that you have a lot of pairs of antennas that are at different distances and different angles related to your source of interest, and that is helping you sample this plane. And also the rotation of the Earth is what makes these tracks longer. So the way this works, this UV plane is what we call the sampling, spatial sampling in the plane where you are collecting your visibilities. The Fourier transform of this is the point spread function. Okay. If you could convolve the point spread function with the actual image of the source in the sky, you would get this, let's say, horrible, dirty image. That is what we usually get when we observe with an interferometer. The process then is to clean this image in order to understanding well what the UV coverage has been, and understanding well what have been the different interactions or the different components that have made these inaccuracies in the collection of the image, recover as much as possible the actual image of the source. And as we say, the benefit of this is that all the detail that you can get in this image is impressive, and also the fact that you recover, let's say, a picture. a picture of the source that you had missed when you used an antenna, because the antenna was only sensitive to one point in the sky. In this very specific case of BLVI, you get again a picture, but the picture, the field of view of the picture is very small. You get a picture of high resolution, but of a very tiny part of the sky. Well, this is how the BLVI networks are organized. This is the specific case of the European BLVI network, the EBN. It has 22 radio telescopes distributed mostly in Europe, but also in Asia, China, Korea, also South Africa, and until very recently, the big 300-meter dish in Arecibo. It is the only, at this moment, network in the world. There are other networks, but this is the only one that works in real time, meaning that the data of the antennas can be sent to the correlator, the supercomputer that combines and produces all this combination of telescope baselines. This correlator is at Jive in the Netherlands, and this can be sent in real time by internet. So in that sense, it's the only network that can do this, what we call the EEVN. It runs at all these frequencies that you see here. Of course, the 21 centimeter line, 1.4 gigahertz of hydrogen that we said before, but also all these other lines in which you can see lots of molecules, OH, methanol, SiO, water, but also, of course, the continuum that can be recorded with all. And with this, we synthesize a telescope that is at large at the Earth. And this is the typical, well, not the typical, this is the best UV coverage that one can get with this network that, as you can see, it resembles quite a lot a fully sampled aperture that you would get with a single telescope. But look at the scale. I mean, we are talking here of mega lambdas, and if a lambda is 1 centimeter, we are talking here of, as we say, a telescope that is as big as the Earth in this respect. This is how Jive looks like. Jive is the correlator, the supercomputer that combines these signals. And also it provides the user support, very important, and technical developments for the network, for the EVN. Jive is an ERIC, and ERIC is an European Research Infrastructure Consortium. It is a legal entity, and it is, the partners are the countries. We have now these 7 countries that are the Netherlands, Sweden, France, the UK, Spain, Latvia, and Italy, which are supporting Jive on behalf of the EVN. And also with collaboration from Germany, from China, and from South Africa. Okay, now let's go a bit quickly about some of the examples in which BLVI has made an essential contribution. This will be both in the extragalactic, but also in the galactic areas, and maybe other areas that could surprise you, I hope. So for the BLVI science, I would start with this study of the innermost regions of AGN. This means, as you see here in the right, and you have some references that you may, if you are interested, you may look for further information. You have here in the right what happens when you look at the center of an AGN, an active galactic nuclei galaxy, with different BLVI networks at different frequencies. So the VLA is a connected interferometer in New Mexico in the USA with a maximum distance of the order of 20 kilometers. Now, BLVI, as we say, thousands of kilometers at 18 centimeter, can make a huge zoom into the inner part of this huge image, in which we expect that there must be a reason for this object that has this center to be expelling all these huge jets of this huge scale. But we don't see in the first image what the reason is. When we go to the highest frequency, we start dipping into the inner core, and higher and higher frequencies, we go to more and more detail, and we are able to resolve the let's say, the surroundings of the big object that is cause of this emission. In these images, we still haven't seen the central, the very central area, and in particular, what we expect that there is a black hole. But we have seen already a number of other effects. For example, this is a very nice study that happened some years ago in which you could track 1 month at a time the evolution of the different components of this jet in these galaxies, 3C120 at 22 gigahertz. And you could see how the different knots were moving actually at an apparent speed that is faster than light, superluminal motion of these components. This is explained here in this cartoon in the left by actually a projection effect. It's not like any of these moves at higher speed than light, but it is true that already it gave a lot of information on how this emission was progressing. But the very well-known result of BLVI in recent times has been this image, the image of the surroundings of the black hole, supermassive black hole at the center of M87. This was obtained recently by the Event Horizon Telescope, which is a project that uses these telescopes, these radio telescopes distributed around the world. And it is a BLVI instrument. And it was able, the team of almost 400 scientists was able to retrieve this image that shows actually the photon ring around the inner black hole that you still don't see. You see the region around it. And it's now calculated, estimated that the object in there has 6.5 billion solar masses, 605,000 million, and it is located at 55 million light years from us, which means that this image has an angular diameter of 42 micro arc seconds, which is really state of the art. It would even be almost incredible just a few years ago to think that this would be possible to do. And this has been achieved thanks to this collaboration and also by using the highest frequencies, highest that typical BLVI networks, in order to reach this kind of resolution. Also, the very recent result that just came out a month ago is the fact that the polarization in this region has also been measured, and this is represented here in this graph. So the image of the surroundings of the black hole gets very well complemented by all the other images that have been obtained by the different BLVI and other campaigns, and it is represented in this graph. So all then complement, and they bring the information from the optical, they get the information. This is the EVN, specific EVN map, in which you see the central area and the jet, and also the other BLVI results that, as I say, are complementing this image. A beautiful, really beautiful result. So, but there are many other things happening. For example, BLVI has been able to locate the area in the sky where gravitational waves have been detected. This is an example of an incredible collaboration in which more than 30 many telescopes got together. The gravitational wave have been detected by the LIGO and the detectors due to the merger of two neutron stars, this event, the gravitational wave 1708-17, which became then the electromagnetic counterpart. That is what we in BLVI we can observe. It's only when there is electromagnetic counterpart. And then this was done with this impressive network, and it came out to demonstrate what had been the detection of this effect of a gravitational wave and the emission in radio waves that happened just after the event and came beamed towards us. That's why we could observe it with this network. So this is actually a very nice complement of how the different areas of astronomy these days are so well merged together, and you have to master or actually have access to all these techniques to really understand the problem better. This is also one of my favorite images from the BLVI, and it is a gravitational lens. In this case, what we see is the distorted image of a faraway object, in this case a galaxy, and it is distorted because in the way between the galaxy, which is here, and us, which are here, there is a massive object that we don't see, but it creates distortion in the gravity field, and it means that the photons that were going well, to miss the Earth in this direction are bent due to this gravitational disturbance, and we are receiving them as if they were coming from these directions, different directions. So what we see is, in this case, a ring of emission that is actually the distorted image of the real object that maybe we don't see, that should be somewhere here. The very impressive thing in this image is the quality. The quality, when you look into the detail of each one of these components, you can actually see, maybe not in this image, apologies, but you can see it in the original paper, you can see how the actual structure of the background object, this galaxy that was here, you can see the spiral arms, parts of these arms, and you can see the structure in the distorted image. And that gives you a very powerful tool to understand what is the object, this massive object that is producing the gravitational lens effect. Another one, the gamma ray burst afterglow. In this case, this was detected by the EVN. It's called an orphan afterglow because actually what we saw, as you can see here in this cartoon, is that once the let's say the cataclysmic event that would have created the gamma ray burst was produced, we actually never saw the gamma ray burst, but what we saw was the effects in the surrounding media. We saw the afterglow and we could detect it, and this is why it was then interesting to study with BLVI. We could pinpoint the position of this event, even if in this particular case there was no counterpart in gamma rays. A very hot topic these days in radio astronomy is fast radio bursts. Fast radio bursts are very short, much shorter than a second, very bright emissions. And we think very bright, and still we don't know what it causes them. Of course, there are some models. But the case is when you observe these fast radio bursts and you see them at different frequencies, you actually, the time in which you observe at different frequencies changes slightly. There is this dispersion, and you can account for this dispersion on the medium that is between the origin of this radio burst and ourselves, and the amount of electrons that exist in this medium will be delaying the radio wave, and this is explained partially by the known interstellar medium. But for this specific this is the Lorimer burst that was the first one detected. For this case, it is quite clear that the whole dispersion cannot be acquainted by interstellar medium. It must be an extragalactic origin. And if it is an extragalactic origin, what means is that this emission is extremely bright, really bright. And this is why it is very important to know where it comes from and what is being originated. And the EVN in that sense, and BLVI in general, has done a lot of contributions because it's capable to pinpoint what specific region in these faraway galaxies the fast radio bursts are coming from. And there are many fast radio bursts being observed. Some of them are repeating fast radio bursts, which are extremely interesting because you can actually start pointing to the right position in the sky. And out of those, there are, of course, different models. We talk about magnetars, very high magnetic field neutron stars, but also there could be other possibilities for this. But it is extremely important, as we say, to be able to pinpoint in the sky where this emission is coming from. This other event that BLVI is capable to trace, the tidal disruption events. It all started with what looked like a supernova. When it was looked with BLVI, the emission that was observed, as we can see here, how it changes in a matter of years. It was tracing the jet that is produced when an object, a star, is engulfed by a black hole. So the star is disrupted by the huge gravity, and the matter is being ejected in this jet, and we are able with BLVI to track in a few years' time, which is very impressive. We are able to track the evolution of this material, and therefore we are able to identify this emission as a tidal disruption event. For more information, as I say, I hope the presentation will be distributed later, and you can track all these news, for example, in the GIAC website. Well, I'm getting now into the area of masers, and I have to run because it's a bit late. The area of masers, as we said before, is when you have this very bright emission associated to some molecule. It could be OH, water, it could be SiO or others. This is very bright, but it's also very compact. And that allows the masers to be used as tools for a number of things. In this particular case, this is a maser in the galaxy NGC 4258. The water masers, when they were mapped and they were tracked, could help model very well the distribution of matter and the structure of this galaxy. And since it is very far away, it also allows to measure very well the distance, and also put some constraints on the measurement of the Hubble constant and constraint of dark energy. This result has some years already, but this technique is still being used because the technique has proven to be extremely useful for this. But masers can be observed in faraway galaxies, and they can also be used to understand better more nearby objects. For example, the stars, star formation regions, in this particular case, it is Orion. You can observe the spectra, or in this case, water again, and you can see how the spectra gives you both the map gives you the structure, and the spectra gives you the velocity. It means you are able to measure in 3D what the structure of these objects are, and then you can also try to understand better what is the link between, in this case, the disk and the inner part of this star forming region in Orion, and the jets that are being ejected, which is part of the whole model of the star formation mechanisms. The case of all the stars has been presented before. This is what we said, the circumstellar shells around asymptotic giant branch stars. These stars have a degenerate CO core, but then they have a very extended atmosphere. And in this extended atmosphere, as the temperature gets down and with the right density and composition of this envelope, you have lots of molecules. And in particular, you have molecules that are masing. You have SiO masers in the inner part, you have water masers farther away, and due to the photoionization by the surrounding media, you have OH masers at the very outside part of these stars. And this is a very nice video that shows what is the evolution of the SiO maser distribution when you observe it with BLVI. And each one of the frames in this movie is 1 month. So if you observe the star, the envelope of the star, once per month, for let's say more than a year, that is the typical pulsation period of these evolved stars, you can actually trace very well what are the conditions and the movements of the material within the inner part of this envelope. Therefore, trying to understand better what is causing the mass loss in these objects, and the whole understanding of these processes in all stars. There have been some new very exciting results in the maser studies, and in particular, this is called the masers superburst. Superburst meaning that when you typically have quite bright masers of the order of 100 Janskis, suddenly one source can go up to 14,000 Janskis. And this happens for a short duration in time. Now, there is an organization called the Maser Monitoring Organization that has radio telescopes all around the world observing these masers. And then when there is a superburst, BLVI is triggered and is capable to make high resolution images in this case, star forming regions, and in this case, water masers. Okay, well, I'm almost finishing this part. This is about astrometry. The fact that you can pinpoint so clearly the position can be used to measure distances, because as we said before, if you are able to track for one orbit of the Earth, the position of an object, which is not too far away, you can measure the parallax, and then you can measure the distance with very high accuracy. And this is a distance to Orion that was obtained by BLVI techniques. And the same can be used to track the structure of other objects in the galaxy, and therefore this is used to map the spiral structure. And there are BLVI instruments that are built explicitly to do this astrometry studies, which means very high accuracy of many objects in the galaxy in order to track its structure with high detail. This is also being used for pulsars. I'm sure Ioannis will have loved this result. And this is how it was possible to track a pulsar with BLVI, and the measure of the parallax, 0.16, was corresponding to a distance of 2.3 kiloparsec of this pulsar, and it was much better tracked with BLVI than it would have happened if we would not have used the parallaxes. So in that sense, it is again a good contribution of BLVI to the field. I think this is almost my last astronomical or science contribution of BLVI. The fact that you can use BLVI not only to observe cosmic objects, but to observe planetary probes, satellites that are being sent to the solar system, in particular to Mars, Venus, or even Jupiter these days. You can track them with BLVI. And when these satellites fly by or get close to one planet, maybe crossing its atmosphere, you can actually get a lot of information about the structure of its atmosphere because of the high resolution you get in pinpointing the position of the satellite. This is called near field studies, and it is of great interest to space agencies, as we are part of several of these projects like Venus Express, ExoMars, Colomer, and more recently JUICE, the mission that will fly to Jupiter and the icy moons already next year. This is not astronomy, this is geodesy. Just a second to say that the same BLVI technique is used often to understand better the Earth. If you have a network of BLVI telescopes around the Earth and you select carefully the targets in the sky, you select objects that are that don't show, or you understand the structure, for example, distant quasars that look point-like, you can use this technique to locate, to calculate the position of the telescopes with very high accuracy, better than 1 centimeter. And that allows you to track these movements of tectonic plates, also to model the different rotation parameters of the Earth, Earth rotation, position of the pole, duration of the day, which are very important for many applications, and in particular for navigation. Even the GPS constellation needs to know the value of UT1 very accurately, and it is BLVI, the only technique that provides it nowadays. Therefore, another nice contribution of BLVI. Now, what for the future? This has to be just a second to say, well, the EVN has made an intense effort recently, and you can download this document called the Scientific Roadmap of BLVI for the next decade. And it explains with a lot of detail what BLVI is contributing to these all areas that I have just given a very short glimpse with a few examples, and how the key science goals for BLVI are to help understand and answer all these questions. So I invite you to download the document that is in archive and take a look at it. It's 170 pages of very nice science. Many of the examples I've given are obtained with the EVN, the network of BLVI telescopes, which is based or hosted in Europe. But there are other networks. There's one in the US, the BLVA. There's one in Asia, the East Asian BLVA networks, in Australia. And there is now this concept of a global BLVI alliance. And why I mean this? Because I think it is very important to know that this is a working group in the IAU, in Division B, and anybody who is interested in exploring how BLVI can contribute to their research should join this working group. And I hope that in that sense, you can track in Twitter and also on the IAU website the details, or get in contact with me for this. Okay. Well, I would love to see BLVI being developed in Greece. One possibility is this antenna that exists in the Thermophile satellite communication station. It is a 32-meter antenna that is no longer used for communications, and it is not a rare case. Actually, there are lots of these communication complexes all around the world. And many of them have been considering to refurbish their unused antenna into radio telescopes. Now, let me mention the successful case of Ghana that was refurbished a couple of years ago, well, a few years ago, and now it's a radio telescope in Knutunse. Also, the African BLVI network in general, which Ghana is the first one, and also in relation to the square kilometer array, the square kilometer array, the SKA, which is being constructed as we speak in South Africa. And it counts on these antennas to expand and also build capacity in the countries in which the rest of the antennas will be built later in the second phase of the SKA, let's say a decade from now. The same concept happens in Latin America, which is this initiative called the Initiative for BLVI in Ibero-America, which is the IVIA, in which antennas in communication complex all around South America are being considered to refurbish as radio telescopes. So I think it's a very nice opportunity, if it's possible, to get this radio telescope working, and it would very, very welcome in the EVN, of course. Well, there are other things. Sorry, I cannot stop much. This is another network called Lofar. This is for much lower frequencies. The low frequency array, which is developed by Astron in the Netherlands. And it has lots of synergies with the EVN. These are completely different antennas. These are, let's say, low frequencies ones, dipoles and phase arrays. But what these are in synergy with the EVN is that many of the EVN observatories also have a Lofar antenna, which is also an interesting opportunity to explore. So I invite you to keep in touch with BLVI. The easiest is next week, when there is the EVN Symposium and Users Meeting that is online with free registration. Please take a look at the link. And also this week, there is another of the EVN e-seminar series, in this case about astrometry, tying the sky to the ground, by Ivan Martí Vidal, also in YouTube on Friday. So please keep in touch. And I now, even if it's a bit late, I hope we have time for a couple of questions. Thank you very much.
Thank you very much, Paco, for this very detailed presentation about everything that we can do with VLBI. There is one question from, hold on a second, from Ming Yang, where he states that the detection rate of extragalactic water masers is actually very low, 3%. Is there a better way to detect them?
Yes, actually, I think I was a kind of in a trap because I was invited to talk in the extragalactic session. Okay, so I tried to fit extragalactic masers in my talk, but he's very right. I mean, for the case of masers, there have been very few detections, mostly OH and well, mostly it's water. Okay. And the reason is that, of course, when you go to extragalactic distances, I mean, you can expect the monster that has to be feeding these masers, how it has to be observed by us. Okay, so I think it's still a rare event, but when it happens, it is a very powerful way to measure the distance to these objects. And they fit very well, as you had seen in the modeling of the maser position with this, let's say, with these curves of position velocities. You can see that they fit very well with the model that you would expect for that distance. It's, as I say, a very powerful tool.
Okay, thank you very much. We still have time for a few more questions. If people want to raise their hands, you should be able to open your microphones now, if you want. I don't see something in addition in the chat. Oh, there is a raised hand. I don't see who the person is. Oh yeah, Yanni Misrilis. Yanni?
Yes, hello. Thank you for the nice talk. My question is, what is the angular resolution that can be reached with the EVN network?
Yes, well, you can imagine, as we said, it depends on two factors, the distance between the telescopes and the frequency, okay? So you can imagine, for one thing, that this is a global network, so you can reach distances of, say, 8,000 kilometers regularly, and it observes typically up to 22 gigahertz, and maybe many times, sometimes at even 43 gigahertz, okay, which is not so common for the EVN. So with that, you can go to sub-millisecond second resolution. The EVN often collaborates with the other networks like the BLVI, and this is the global BLVI. We call it global BLVI. And then, of course, you can reach even larger distances of, say, 10, 12,000 kilometers in baselines. So yes, I think that is more or less the limit. If you want to go to micro seconds, as we see in the case of the HT, you really have to go to much higher frequencies that are not available for the EVN.
Thank you.
Okay, thank you. Since I don't see any other hands raised, I would like to thank once more Paco for being with us virtually. We hope that we will have the opportunity to invite you in person to come to Greece soon for another science meeting. And I would like to encourage everyone, if you wish, to just sign off from here and then join the corresponding session you wish to join. If there are technical issues, the IT person will help you. Okay. Thank you very much again.
Thank you. Bye-bye.
Bye.